Hi everyone. In this video, I'd like to talk about a claim which says if G and H are finite groups and phi is a map from G to H is an isomorphism, then the order of X equals the order of phi of X. All right, so let's just take a look for a moment at a picture. So this is going to be my group G. Now recall that G is a set together with a binary operation. So let's assume our binary operation over here is star. All right, so that's my group G. And then over here on the other side, I've got a different group. I'm going to call this group H. And H is a set together with binary operation, squiggle face, cat face, could be anything you want. I could call it a plus sign if I want. I could call it a shoe. I could make up any symbol that I wanted to and then define it as a binary operation, and I'm good to go for it to be a group. So we've got this map phi, and phi goes this way. So if we've got an element in G, I'm going to label this X. When we phi it, we end up over here in H. So we end up at some element in H. I could call it, little h, but since it came from X and it came from phi-ing X, I'm going to call it phi of X. But I want to emphasize that X lives in our originating group, our domain, our G, and then phi of X lives over here in a set H. Okay, so we've got a picture of that. Now, what I want to talk a little bit about is this concept of being in order. So we're talking about these vertical bars. So when we say that the order of X, and that's what I mean by those vertical bars, the order of X equals n, and I'm going to assume that n is less than infinity because we've got finite groups. I can't have any element of infinite order, something sitting in a finite group, and you should think to yourself, why is that the case? What theorem am I using? But anyways, I've got an element, X, and it's order n. So what this means is, so the order, sorry for my handwriting there, that was a bit messy, but I'm on a tablet here. Order of X is n. What that means is it means that X to the n is the identity, and the identity in G, and that's really clunky notation, E sub G, so I'm just going to call it a 1. Now keep in mind, we've got identity elements that are indeed 1. We've got identity elements if it's an additive group that could be a 0. So that identity element, who knows what it is, but I'm just going to write 1 for ease of notation. But if you really like E sub G, go ahead with that. So that's one property of being the order. And what that means here is that X star, X star, X star, if I do that n times, right, that's what it means to raise X to the nth power. It doesn't mean to multiply, it means do the binary operation here. If I do that n times, that's what's giving me the identity. So that's the first property of being the order n. So X is order n if X to the n equals 1. And very important, n is the smallest power that will do this. And I'm just going to write loosely, that works. That gives us the identity. All right, so you've got two important properties to keep track of here. The first one for the order is that X to the n is 1, and the second important property is that it's the smallest exponent that will do that. Okay, so two important properties of the order. So let's go ahead, set up the proof, and then talk about some strategies for proceeding. Okay, so this is a conditional statement. I want to emphasize a few things here. Everything between the if and the then. So this is what I need to state for my assumptions. Okay, so I'm going to write that down. Proof. Assume G and H are finite groups. And I'm going to assume phi goes from G to H is an isomorphism, which I've abbreviated there. Now, I need to show that the order of x is equal to the order of phi of x. So let's assume that the order of x is n. N is some finite number. So this implies two things. Let's squeeze the information out of the definition. Number one, it implies that x to the n is equal to the identity in G, or if you want to just call it 1, I'm totally cool with that. And if x to the a equals 1, in other words, if there's some other power that also gives us the identity, we know that n is the smallest, so n is less than or equal to a. Okay? So now we're really interested in showing that phi of x has order n. That's what we need to show at this point. All right. So again, to show that, what we need to show, and this is where I'll leave you, so you need to show, again, these two properties of being the order. Number one, you need to show that phi of x, all raised to the n power. Now remember, this is an element in H that lived over in H. You need to show me that that raised to the n power is the identity in H, or just call it 1. The identity, whatever you want to call it, 0, I don't care, whatever you want to call it, the identity. So you got to show me that phi of x raised to the n power gives you the identity. And that's not too bad. If you use the properties of homomorphisms, you can get to that result. And then the second thing we need to show is that if you've got some other power that gives you the identity over there in H, then it was the case that n was the smallest exponent that did the trick. All right, so some hints to think about. You've got properties of homomorphisms. So if you're going to phi something like x to the n, that's the same as phi of x n times. That's the same as phi of x n times. That's the same as phi of x to the nth power. That's by properties of homomorphisms. So something along those lines is going to be very helpful for finishing up this proof. All right, I don't want to ruin the surprise for you or give you the answer or take away the thrill of the hunt here. So I'm going to leave it at this point. And if you have questions, definitely contact me or whoever your instructor is.